welcome to the last talk of the morning of the day for today. Our speaker is Maral, who is going to tell us about algebraic invariance of blow-up algebras arising from ladder determinantal modules.
Okay, thank you very much. Before I begin, I would like to say a big thanks to organizers for giving me this opportunity and for making it possible to be together. I'm gonna talk about the algebraic invariance by focusing on special fiber, and just because I am the last speaker to keep you refreshed and engaged, I am doing advertising. Okay, I will give you a method to calculate the regularity of a special fiber with your hands and faster than Macaulay too, and also a formula for the multiplicity. So this is based on the joint work with Alexandra Costantini, Luisa Fulli, Kriti Goel, Quenoan Lin, Heidi Lindo, and Whitney Liska. Okay, so let's go. I'm gonna take advantage of the slides of Lin and just recall you that we are focusing on the special fiber of module. We are on the ring, polynomial ring K of T over the fiber ideal. So we have its initial algebra, we denoted by f of n, and it is also living in the same polynomial ring, but the ideal of definition is denoted by k star. So they are Bleuker type binomial relations because they are algebra over monomials. So as a remark, the initial of k star is a square-free monomial ideal because they are coming from the Bleuker, and this is the Grosvenor basis. So we have a square-free monomial ideal. So we remember the result of Konka-Barbara 2020. As far as the initial ideal turns to be a square-free, so the ideal and its initial shares the same extremal Bethe number. So what does it mean? It means that they have the same regularity. They have the same project dimension. They have the same depths. And we know that even for simple examples of ideals, when we don't have square-free initial ideals, we can get this equality for the regularity. They don't have the same regularity or depths. Okay. So all of our methods are by Sagby and Grosvenor-based deformation to get the regularity. So what is the idea? We have a special fiber and we have its initial. By Sagby, we know that a special fiber and its initial algebra, they have the same Hilbert series. And thanks to the talk of Tina.
Can I ask you something? In general, the initial of the fiber is not the fiber of the initial.
Never. Never, no. Just in the case, no, yes, yeah, no, not never, no, not never. But it is just the case to have a Sagby basis. If you can find, if the generators are Sagby, so the initial of algebra is exactly at the algebra generated by initials. Yes. But it is really rare.
Very rare.
Yeah, it's really rare. Yeah. Something like it is the same as if you have generators of the ideal. Is it the Grosvenor basis or not? Yeah. In many cases, not. So yeah, we have to find the Sagby basis to go from the initial algebra to the algebra of initials. So it is because by the work of Lin and Shen, we know that these generators are Sagby, so we can go to the initial, the algebra of initials. So because we know that now this algebra and its initial have the same Hilbert series, so and they are Cohen-Macaulay rings, so we have this property that the regularity can be read from the degree of numerator of the Hilbert series, as Tina talked today. So the regularity of this special fiber can be read from the numerator, the degree of the numerator of the Hilbert series. So it is the same as the degree of the numerator of the Hilbert series of the initial algebra because they have the same Hilbert series. So instead of calculating the regularity of this special fiber, we just calculate the regularity. You can just calculate the compute the regularity of initial algebra. But even more, we have K star and its initial ideal. So we know that this is a square-free monomial ideal. By the result of Konka-Barbaro, they have the same regularity. So instead of calculating the regularity of a special fiber, you just can go and focus on this quotient ring over the initial ideal of K star. Remember that this is an Stanley-Reisner ring associated to a simple initial complex. So what do we know is that we have a Stanley-Reisner ring. The regularity of a Stanley-Reisner ring is nothing else than the projective dimension of its Alexander dual. So even we don't calculate this regularity, we just go directly to the Alexander dual and we calculate the projective dimension, so we get the regularity. So it is an idea. So it was the idea and approach. So we have a square-free monomial ideal. So we have very powerful combinatorial aspects come across. So what are these? Let's name I as an initial of the K star. It is a quadratic square-free monomial ideal. What does it mean? It means that we have a flat complex. Each flat complex is corresponding to the clique complex. So we have a simple graph that the clique of this graph are exactly faces of this complex. What does clique mean? It means that complete subgraph. It is a clique. So the facets of this simplicial complex are exactly maximal clique of this graph. But it's not all. We have more aspects. I is a quadratic square-free monomial ideal. What does it mean? It means that it is an edge ideal of a graph. What is this graph? It is a complement of the same graph. So summing up, we have I. It is the initial of K star with respect to some specific monomial order. So we have an ideal of a Stanley-Reisner ring corresponding to the clique complex, and in the same time, it is an edge ideal of the complement of the graph. So it is not all. We have another aspect. We have a set of the minors. So we have a poset partially ordered. So you can put it in the distributive lattice. And this distributive lattice is nothing else than the ordered simplicial complex. So this simplicial complex actually is a clique complex and at the same time ordered simplicial complex. What does it mean? Any chain is a face. So maximal chain are facets. So maximal paths or chain are exactly the maximal clique of the same graph. So we have graph theory and lattice theory, and we have this simplicial complex theory, and all of them together help us to find out what is the projective dimension. Example. So suppose that we have this example. So just to get what is happening. So you can consider this two-sided ladder. These are the generators. Exactly, this is the number of the columns corresponding to the generators. There are T variables that we want to explain the special fiber. I consider just one layer as a quotient over K. What is K? It is a Puluka relation. This is 5 Puluka relations for this ideal, each of which, for example, this is T23, T14. These are 2 minors, 2, 3, 1, 1, 4. They are incomparable. And exactly they are leading terms of these Puluka relations. So they are exactly giving us the initial ideals. What is K star, which is the defining ideal of the algebra of initial? They are binomials here, exactly the first binomial that you get here, the incomparable one, and you can see this is the minimum and the maximum among the indices, which we call it join and meet. So this is K star. What is the initial of K star? Is exactly the product of the first 2 indeterminates corresponding to the incomparable matrices. So what is the graph? This is the G complement. Look at this graph. Yeah, it is tiny. So we have 1, 4, 2, 3. So we have the generator 2, 3, 1, 4. And we have, for example, 2, 3, 1, 5. So it is an edge ideal of this G complement, if you want to see. And we have also the lattice, which is the clique complex. In this clique complex, if you get a path, start from here and go to the up, we have a single minimal element and the single maximal element. And if you look at this path, this is a maximal clique. What is the complement of this clique? This is these 3 elements, goes to the G complement, turns to be a minimal vertex cover of G complement. This is a minimal vertex cover. What does it mean, minimal vertex cover? A vertex cover is a subset of the vertices that you have, and this subset cut at least one of the vertices of each edges. You take one edge here, it involves 2 vertices, at least one of them is there. So it is a vertex cover, but we consider a minimal among all of them. So it means that it's minimal with respect to the inclusion. So it is a minimal vertex cover, covers all of the edges. So it's corresponding to this maximal clique. Why it is important? Because it is related to Alexander dual. Alexander dual is generated by exactly the product of these T variables coming from one minimal vertex cover. And we want to explain what is the projective dimension of this. So summing up, we have minimal vertex cover of G complement. So it is exactly corresponding to Ti when I comes from the out of the facets of this completion complex, each of which are corresponding to maximal clique. They are not the same. They are in the 1-1 correspondence. And also we have Alexander dual. Alexander dual is generated by the product of these T variables comes from one minimal vertex cover. If you can find all of the minimal vertex cover, product all of these T1s, you have all of the generators of Alexander dual. We have one more aspect. Again, we have a square-free monomial ideal. Concal-Barbaro implies that the Cohen-Macaulay-ness of the algebra goes to the initial. The Cohen-Macaulay-ness of ideal goes to this initial. So because we know that K star is Cohen-Macaulay, its initial also is Cohen-Macaulay because this is a square-free. So I is a Cohen-Macaulay ideal. So the associated simplicial complex is pure. What does it mean? It means that all of the facets have the same dimension. What does it mean? All of the maximal cliques have the same cardinality. What does it mean? All of the minimal vertex cover has the same cardinality. And what does it mean? It means that the Alexander dual is generated in single degree. So all of them have the same degree. So what is this cardinality? What is the degree of generators of Alexander dual? This is the same question. So it is another result. It is nothing else than the analytic spirit. So they are generated by the degree of the analytic spirit, or it is the cardinality of maximal clique. Cool. But another result that we get is that linear quotient property. That's a very nice property that also he mentioned in his lecture last week. So we could show that the Alexander dual is generated, and we have a linear quotient order over the generators that they are linear quotient property. They have this property. What does it mean? It means that you can put an order over the generators of Alexander dual such that the successive quotient ideal, the successive Kuhn ideals turn to be generated by the linear forms. But because we have a monomial, so it means that these successive quotients actually are generated by variables. So we have this one. Okay, cool. Linear quotient property is a nice property. So it means that the ideal has a linear resolution and we can determine the Betti numbers. Specifically, last Betti number, which gives us the projective dimension. So you can see that the book of Herzog-Hebe, the projective dimension is exactly equal to the maximum number among the generators of Qi. So if we determine the number of generators of Qi, the maximum number of generators is the projective dimension. So, and another thing, so it is the projective dimension, but you can ask about the last Betti number. Okay, so the last Betti number is exactly equal to the number of the occurrences that these quotients, these successive quotients reach to the maximal possible one. So this is the last Betti number. So you can ask for a Gorenstein or it's not, if it's one or it's not one and something like that. Okay, cool. Okay, our purpose is to find the projective dimension. Life is not that easy. We have 7 lemmas, and even we have lots of notations, definition, and something like that, so to get the projective dimension, because it's really technical. But I just explained it to it by an example. But what does it mean? The result. So you have, and my promising that you can calculate by hand the regularity or projective dimension. So we have this matrix, as Lynn explained. The length of non-zero entries here is 3. The length of non-zero entries is 2, and the length of non-zero entries is 1. So 3 plus 2 plus 1 plus 1 is 7. This is an analytical spread. It is the cardinality of maximal clique. Look at the distributive lattice. The distributive lattice is started from 1, 3, 5. This is the unique smallest one. Well, it doesn't work. And we have the unique 4. It doesn't work. Yeah, I would like to, maybe I can use it. Can I use it as a laser? Okay, yes, okay. So this is the unique maximal element, which is the 4, 5, 6. Each maximal pass starting from the point A, let's say to B, is a maximal clique or is a maximal pass. but which one unveil the projective dimension? There is at least one that unveil the projective dimension. What is this? Okay, in each spot we have n up because we are not in the 2 by n as you asked. We are in n by m, so we have n up. For example, we have a triple here, and we have 3 direction, E1, E2, E3. So by E1, you go from 135 to 235. By E2, you can go 145, and by E3, you go in 136. So look at the lattice is really complicated, but you can write it, the maximal clique, as a table, which is a standard table. This is the maximal clique denoted by this. What does it mean? You start from 135, which is the smallest one, and you end with the maximal one. But in each step, you go with one of these directions, which must be legitimate. What does legitimate mean? So it is 7 levels. So it means that you cannot go always up with all of this possibility. For example, here, there is no E3 direction. So it must be legitimate. But if you go from 135 to 235, you go by E1, but we just codify it by 1. We don't say E1, it means that 1, and after that by 2, you go to the 245, and you go by 3, you go from 245, you go to 246. So it means that the direction is E3, but we just write it 3. And after that, we have E1, we just go E1, and here we have E2, and we have E1. So instead, to show you the maximal path, instead of writing this table as the maximal clique, we just write the 1, 2, 3, 1, 2, 1. And you know exactly what is this. It is determining the maximal clique. But what is important here? This is a strictly increasing index. In each step that you are going up, take the smallest possible one. So if you do this, you have 1 strictly increasing sequence. You have 2 strictly increasing sequence, and you have 3. So 1, 2, 3. This is a sequence index, and this is the minimum possible one for this matrix. And this is the maximal clique that gives you the projective dimension. So we know that what is the analytic spirit? The projective dimension of Alexander dual, which is exactly equal to the regularity of this Stanley-Reisner ring, which is equal to the regularity of a special fiber that we would like to determine, is nothing else than the analytic spirit minus 1 minus the sequence index of this maximal. So you know you will write the maximal clique, and in each step you take the minimal possible one, in a way that we have the sequence index being a minimal one. Actually, this is when you choose another maximal clique, it is the number of generators of the successive quotient ideals. So it is the minimum. It is a maximal among them because we subtract. So, okay, as a corollary, we have for free. Now we have an invariant of a special fiber, and we have the reduction number. And we expect that the invariant to be a negative number because Lin and Shen, they have shown that they have rational singularities, so the invariant must be negative. And this is example. So the regularity is 3, the invariant is -4. We can recover the same results for generic matrices. We consider this ladder, two-sided ladder determinantal rings, which is equivalent to the Grassmannian, to the generic matrix. What does it mean? It means that up to the initial ideal, they have the same initial ideal. So we reduce it and put it these zeros. Okay, so the sequence index is always the size of matrix is n and m. The sequence index is always m-1. So we have the regularity for Grassmannian, and we have invariance. Of course, it is not a new result. It's just recovering the noun results. Bruns, Herzog, 1992, they showed that the invariance is -n, but their approach was using the algebra of a straight line law. But we are using just the combinatorial aspects here. And the multiplicity, the same idea. The algebra and its initial share the same Hilbert series. So they have the same multiplicity. And again, we can reduce it for the initial ideal. This is the same for the initial ideal. Try in 1998. He shows that, okay, when we have a Stanley-Reisner ring here, so you can consider this. So the multiplicity is exactly initial degree of Alexander dual. What does it mean? The initial degree, it means that the number of generators of Alexander dual of minimal degree. But in our case, the Alexander dual is generated by the single degree. So the initial degree here is exactly Betty 1. It means that the multiplicity of a standardized ring here or the multiplicity here is exactly equal to the number of the maximal click or number of the all maximal paths that you can start from A and go to the B. It is the multiplicity. So the multiplicity must be this number. Okay, cool. What we could understand is that we have our layer. What is the multiplicity of first layer and related to the module? So it is a product of a binomial number. So it means that if we can understand what is the multiplicity of one layer, we have the multiplicity for the special fiber of the module. So we focus on just one layer, but can be calculated by the Ferrer diagram or Young tableau. When you just have a Young tableau and fill it by the strictly increasing numbers, it is a standard. The number of the Young tableau, standard Young tableau, is exactly equal to the maximal click, the number of the maximal click. They are equivalent. So in the case of the Young tableau, we have Hooke-Lens formula that releases the multiplicity, but it would be just for Grassmannian. We would like to find for the two-sided ladder. So what does it mean? That we have a Ferrer diagram, we had another Ferrer diagram corresponding to the 0 spot, and we superimpose. This is the yellow one. And we get a skew-Young tableau. If you have a skew-Young tableau and you fill it in the strictly increasing way, so you have a standard skew-Young tableau, and this is again exactly equal to the maximal click of 3, which we cut this cardinality. The number of these maximal clicks is exactly the multiplicity of a special fiber. The name is a skew-Hooke-Lens formula. For example, we have this example. This is a superimposing, this is a skew-Young tableau. We superimpose here, and this is the number of the hook. The hook, it means that you have a cell and you count just all of the cells which are in the right and down sides. So this is 1. For example, here we have 1, 2, 3. So this is number is 3. Here is 3 because there is nothing in the right, but in down 1, 2, 3, we have 3. So the idea is that you haven't, I don't have time, so you have just an active cell and you put it as an exciting move, we get all of the exciting diagrams. And if you put all of them together, you will get the multiplicity. This is the analytic spread minus 1 factorial, and this is nothing else than the multiple of this Hooke-Lens formula. And you just sum over all of the possibility of this excited diagram, the multiplicity is 16. It comes from the result of, actually, it was a result of Morales Panova in 2018. They have shown that for any skew-Young tableau, if you fill it in the standard, this is a number of the filling number. And we could show that, okay, so in this case, our multiplicity comes from exactly this formula. This is for general case. And thank you. This work was started in Vico2 in Trento, Italy. And after that, we went to SLMAS, we went to Berkeley, Summer Research Program 2024 to complete the project. And this was some of the results of this work. And thank you for your attention.